The next speaker of this session is Marco Corgini. Yeah, yes. from the University of Las Vegas.
Yeah.
So please, Marco.
Okay. Anomalous average Bose-Einstein condensation and spontaneous breaking of continuous symmetries traceable. Well, singularities of thermodynamic functions emerging after passing to thermodynamic limit have been identified as critical points of phase transitions for decades. So, not only in the classical case, but in the quantum case too. The basic elements of phase transitions theory are the following ones. We have symmetries, conservation laws, selection rules, all derived from symmetries, give states, thermal average, and anomalous average or Bagalyov average. Ordered parameters, thermodynamic limit, singularities of limit thermodynamic functions, pressures, thermal average, etc. Use the framework which we are located now. In the case of Bose-Einstein condensation, subject of this talk, the spontaneous breakdown in this framework of a continuous symmetry U1 gauge group is predicted by the standard theory. So you know what is Bose-Einstein condensation. We have a lot of particles enclosed in a certain region in the space, and if we are lowering the temperature, many of the particles are located at the ground state of the system. In other words, in the state of minimal energy of the particle system. So we have a macroscopic observation of the ground state. Bose condensation understood as microscopic observation of the ground state as symmetry breaking of the continuous symmetry occur only in the thermodynamic limit from a mathematical point of view, which is real in real physical systems is never reached. Which I contrast this approach to back with experimental evidence obtained during the last years. It will show the example of free Bose gas whose energy operator is perturbated by a nonlinear term preserving the U1 symmetry whose behavior is quite similar to the free gas model coupled with a symmetry breaking term. This will be done in a scenario where both systems should undergo, at least theoretically, condensation dependent on temperature, phenomenon not associated to singularities. In this case, there is no breakdown of the U1 symmetry. However, the system undergoes macroscopic observation of the ground state. This is a formalism of second quantization for one particle enclosed in a certain region in the space, in this case a box in RD. And these are in the 6-point, this depending on the border conditions of the Laplacian, we obtain a discrete set of values for the spectrum. We have a discrete spectrum. It's just the formalism. We are going to write all operators in terms of creation and annihilation of operators. HL is the same adjoint operators on the Hilbert space, Fock Hilbert space FB of symmetric functions, and HL is the free part of the system plus interaction. This is the HE. So we have the Hamilton H, this is the free part of the energy, and this is the interaction, and beta is the inverse temperature, and mu chemical potential, as we all know. So the second quantization of the Laplacian is this one, and of the interaction is this one. And G represents the number of particles associated to the state G, and N's total number of particles. This is the number of particles operator without the first term. Again, speaking, the Hamiltonian has this form when we have interaction between couples of particles, okay, in momentum representation. This is a general representation. Well, this is the partition function, the pressure at a finite volume. This is the volume. This is the energy operator, mu the chemical potential, as I said before. These are at a finite volume. And we are interested in studying this kind of functions in the thermodynamic limit when the BL tends to infinity and the number of particles tend to infinity too, in some sense. This is in the grand canonical ensemble context. If we are interested in the canonical partition function or canonical situation, we can define the partition function. This is a system exactly for n particles, and this is the free energy of the system. This parameter here represents the density of particles, the number of particles here is n, and BL the volume. The given states in the grand canonical ensemble and in the canonical ensemble are respectively these two here. This is the trait, this is the grand canonical thermodynamic sum, and this is the canonical thermodynamic sum. This is the operator H restricted to the space of exactly n particles. The given states are defined in this way. This is observable of the system, a self-adjoint operator, so any kind of operator defined on the whole space. So this is the average of the operator A in this framework, and this is the thermal average of the restriction operator A and to the space with exactly n particles. This is the limited thermodynamic functions, free energy, pressure in the grand canonical ensemble, free energy in the canonical ensemble. These two conditions must be realized, fulfilled. Conservation laws. The Hamiltonians, the energy operators, are invariant under this kind of transformations. These transformations implies this commutation rule, this conservation rules, and the following there is the selection rule. Is this fact holds in the system, so we have conservation law and selection laws. P is any index in the space of momentum, for example. Conservation means that the evolution of operator n, for example, where n is the total number of particles, the evolution of the total number of particles satisfies this equation in a strong way for operators. There are three types of condensation recognized. So condensation of type 1 is which we are interested, macroscopic operation of a finite number of states, including the ground state. What this means? This means that this parameter here is 0 for values of mu less critical value of the chemical potential, and greater than 0 for values of mu greater than this value there. Okay? How we can relate Bose-Einstein condensation and symmetry breaking? So we have to take the same operator, the original operator, which is commuting with n, and we can break the symmetry by adding a term of this type to the original operator. This is a phase, this is a constant, y is a parameter. In this case, obviously, n does not commute anymore with HL. And we define now the limit thermal average defined in this way. This is the so-called Bogoliubov quasi-average or anomalous average. And in this case, we have this situation, okay? selection rules does not follow anymore. How we can relate symmetry breaking with Bose-Einstein condensation? Look at this. This is the relation. Taking this limit in this order, we can prove that this average before, this one, are equal to rho 0, not equal to 0, if the density is greater than critical 1, and exactly 0 if rho is less equal rho critical. You can fix here chemical potential and critical chemical potential or temperature or whatever. From a mathematical point of view, for rho less equal rho critical, in the uncondensed phase, it is possible to make a limited exchange, obtaining this result. And for rho greater than rho z, this is the situation. These are different. Some comments. The non-commutative limit show that any chain perturbation is sufficient to break the symmetries. No real-world system is completely free of external perturbation. Thus, the limiting procedure of maintaining a small external field while taking the thermodynamic limit could be viewed not only as a mathematical trick, but also to good approximation as the actual situation in nature as well. This is the opinion of Bachmann. The introduction of an external field does not explain by itself, however, the broken of symmetry. The notion of asymptotic approximation in this case should be clarified. However, for finite systems and BL large enough, the following behavior should be expected to work. It cannot be determined whether the transition, if it exists, is spontaneous or not. However, once the condensed and uncondensed phase emerge, the thermodynamic limit as an approximation of the real phenomenon far away from critical regions seems to be a suitable scenario for determining numerical estimation for the condensate density and for the other parameter, rho 0, defining the breakdown of symmetry for finite but large enough system. However, this is a conjecture that should be confirmed or rejected on the basis of experimental situation. Conceptually, the necessity of thermodynamic limit is an objectionable feature. First, the number of degrees of freedom in a real system, although possibly large, is finite, and second, for systems with long-range interaction, the thermodynamic limit may even be not well defined. This observation indicates that the theoretical description of phase transition, although very successful in certain aspects, may not be completely satisfactory. Or there are some more declarations, different pro or against. Let me put an example. Let's see, this is the most simple example. We have the energy operator of the free Bose gas coupled with a breaking term, breaking symmetry term, and this is a non-linearity term. Okay? This operator commutes with n, the total number of operators, so the symmetry is conserved, and this one does not commute with n. So, this not commute, so U1 symmetry is preserved, and in this case, U1 symmetry is broken by the external source. We have two theorems. The pressure of the approximate, in the limit, the approximate Hamiltonian is given by this expression, and we can prove the following theorem. In the thermodynamic limit, both systems, that system with breaking term and this system with a non-linearity coincide in the thermodynamic limit for nu less 0, and the amount of condensate satisfies this condition here. So you can see that this result does not depend on temperature. What happens with reality? Why Beck trapped gases is so relevant today? This system constituted by a finite number of atoms respond quite well to experimental manipulation at a fundamental level. Moreover, they can be considered as a kind of bridge between the microscopic world and its macroscopic counterpart. They represent the best theoretical and experimental scenario to analyze a kind of real quantum particle system, not only from a microscopic point of view, but also from the perspective of the canonical example. there is little chance of finding physical phenomena that can be simultaneously both theoretically and experimentally analyzed firsthand, as the case of Beck. It should lead in the near future to a deeper comprehension of general phase transition, of this type at least. Complete what's the case of trapped gases. They are completely isolated finite systems that do not exist. Trapped gases are finite-sized systems. The number of atoms that can be put into the trap cannot be considered macroscopic. This is the order. In the framework of the standard theory of phase transition, Beck and the corresponding breakdown of U1 symmetry exists only in the so-called thermodynamic limit Bose system for at least stable systems. In the presence of significant condensate, interaction effects becomes determinant and dominate as this range of temperatures. In this scenario, the Bose-Einstein model does not describe adequately the system behavior. Trapped systems are spatially inhomogeneous. Beck in quasi-uniform three-dimensional potential of an optical trap box has been studied the last time. Trapped Bose gases can display low-dimensional Beck phenomenon prohibited for infinite Bose particle systems by the Hohenberg theorem. The thermodynamic limit is never reached exactly. To overcome the difficulties in defining pressure for a gas confined in an inhomogeneous trap, it is necessary to define simple macroscopic parameters that behave like pressure and volume. So you have defined a new limit, a new kind of limit. Conventional textbook many-Bose systems are spatially uniform. Ultra-cold gases do not present translationally symmetries. Atomic Bose-Einstein condensates have been obtained for linear or circular traps which are uniform along only one direction while still being harmonic along the other two. Bose-Einstein condensation of an atomic gas in a quasi-uniform potential was observed and characterized. It's very interesting. Both the momentum distribution of the non-condensed component and the thermodynamics of condensation are close to the theoretical expectation for a uniform system, while being clearly distinct from the conventional case of harmonical trapped gases. So we have an opportunity to study uniform system. Recent experiments carried out in quasi-uniform magnetic traps seems to show good agreement with the theory developed for uniform Bose gas. We can test then the traditional theory with this. However, some theoretical results suggest that the observed condensation could be if effectively it exists in the bulk system of the third type. In other words, it could be a generalized Beck macroscopic occupation of the ground state. That's it. Limit process always are a problem for mathematicians and for physicists, I think. Passing to the thermodynamic limit has been accepted during a lot of years, I think 40 years or more, 50 years. But in fact, you can find an extensive literature about this, or the works even now, about existence of ergodic measures in the thermodynamic limit in classical and quantum cases, but unfortunately this limit does not exist in nature, even in the classic case. So all the approaches now are directed to a different way to look at the atom system enclosed.
Just coming back, the Bose-Einstein condensate is usually perceived as a macroscopic node. One of the first examples of phenomena that
Yes.
are predicted by statistical physics that can be observed macroscopically.
This is.
Yeah, so I didn't get exactly what is your philosophical take on this, on the fact that you can scale it to the microscopic level.
The problem is that you are identifying singularities of limit thermodynamic functions with phase transitions. It's not true.
And what is the assumption?
No. If you have, for example, take this series. Let's put here one. You can zoom. This, the finished zoom has no singularity. You have a set of functions which does not convert uniformly to another function, continuous function. This function could be not continuous.
What you're saying is
This is
that
the case.
the mathematical notion of singularity
The mathematical
does
notion
not
of singularity
correspond-
does not explain the phase transition. Because the broken of symmetry is not explained by the thermodynamic limit. Because the rupture of symmetry is possible only in the thermodynamic limit. For Phillips systems, you have no transition in this sense, and you have no broken symmetry.
There is a whole literature on this. Jeremy Butterfield, Bettelman, from the philosophical tradition. And of course you're right that there is a convenient characterization of phase transitions as singularities in the partition function by Ehrenfest.
Yes,
From the 1920s.
you can see.
But of course,
there are
these
there are different opinions about.
These singularities do not
Yes.
correspond to
Well,
anything
this-
in nature. Real systems are always have finite numbers of particles. But nevertheless, one can build approximations.
Okay. That's right. That's right.
There's the whole
So,
realization group approach to phase transitions.
In many sense, it is a very good approach, but this does not represent, physically speaking, the phenomenon. You know what's happening.
But
you don't want-
physics very often relies on
Yeah.
idealizations.
But this is a problem.
Yeah, it doesn't, but this problem doesn't emerge only in, I mean, it emerges of course in statistical physics, and it emerges as well in general relativity, you know, with the metrics and the singularity. It's the same.
It's the same problem.
Yeah.
It's absolutely the same problem. I could do two examples. The Bose gas perturbed with a breaking term, the free gas with a non-linear term. Both explain the same thing. But in one case, there is no breakdown of symmetry. And in fact, in the experiments in trapped gases, breakdown of symmetry, global symmetry, is not detected. It's not detected.
Any other questions? Comments? Thanks, Marco.